Hello, everyone. I hope you can hear me well, and I hope my iPad will behave this time around. Okay. So, let me share my screen with you. And okay. So, because PageRank is so extremely important, before we continue with it, let's briefly review the most salient features of it, right? And there are kind of three types of intuition that the inventors, the Page and the Brim employed, and they are all extremely important and very indicative of how we design such algorithms. So the first situation is a simple one. You want, let's denote by row I the page rank of page PI, right? Then you would want to have the following property, that the rank row I is large, just in case page PI is pointed at, right? So this is page PI. Just in case page PI is pointed by considerable number of other pages, let's call them PJ1, PJ2, PJ3, all the way to some number PJ sub k, right? So you would like that a row of I is large if and only if the ranks of the pages that point to PI have large ranks, and they are reasonably stingy with giving recommendations, namely having hyperlinks to other pages. So they don't point to an excessive number of other pages. And one formula that has this property is that a row I is equal to the sum over all j, k, or j m, say, that point to the page I, okay? Maybe I should put it in a kind of a bit clearer form. I should simply say here that all PJs that point to PI, and then a rank of PJ divided by the number of outgoing links of PJ, right? Because in this way, a row I will be large if and only if the ranks, there are quite a few pages with large ranks themselves that do not point to an excessive number of other pages, right? So now the question, of course, is why just this formula. Why not say rank squared and the square root of the number of outgoing links on PJ? Well, for two reasons. First reason is that whenever we want to model something, especially when we model huge systems such as World Wide Web, we should always try to do it in as simple way as possible, because in all likelihood, huge systems will involve a huge number of complicated operations to compute things there. And so we want to keep these elementary operations that we will have to do as simple as possible. But there is even a better reason why we look at that, that we are going to describe now. So the other two intuitions are you have a surfer that starts at a random web page, follows a link to another web page, right? Follows a link to another web page, and so forth. Doing that a very large number of times, say T. A reasonable way to estimate the importance of a web page is if you do such a very long surfing, what would be the number of times that you visit a particular page PI compared to the total number T of all web pages that you visited. Idea being that what they say, all roads lead to Rome. Rome is an important place because roads in other cities of the Roman Empire were mostly connecting these cities to Rome. So if a web page is significant, it will be well linked with other significant, will be pointed at by other significant web pages. So if you click randomly, you are likely to encounter a link that lead to this web page. So that's another intuition. So it's an intuition that after a long surfing, if you count how many times you visited a particular web page, well, the total number of visitations divided by the total of that page divided by the total number of web pages visited, or the total number of clicks that you made, should reflect the importance of a web page. Okay, another related but different intuition is the following. Rather than having one extremely long web surfing, you can do several things. One thing would be you choose large numbers, say N and T, and you do the following experiments. You start just like above by following randomly chosen links altogether N times, and then you repeat this experiment T times. So this is also N times following the link and so forth, right? And the total number of experiments is this large number T. Now, at the end of each experiment, you can record which web page you ended up at. And then you can So you can find similar ratio in which the number of times, so number of times endpoint was pi divided by the number of experiments t. And the idea being again the same, that if a web page is important, then it's very likely that after n serves, it's more likely that after n serves, you should end up at that web page than one that is less important. Of course, for these two heuristics to make sense, clearly these ratios, right, should be independent on the particular choice of links. And if you let t and here n and t to grow large, they should stabilize, they should converge to some fixed numbers, right? Of course, the question is, given the structure of World Wide Web, why would this number converge at all? Well, in fact, they won't. What's the reason for that? The reason for that is simple. Okay, what is happening here? For example, if in surfing the web you reach a PDF document, then you will be stuck there because there will be no outgoing links. So this would preclude these numbers from converging. And as we mentioned, also, if you have a large group of web pages that have that form a connected graph in terms of the hyperlinks and have incoming links out from outside the group, but they have no outgoing links at all, then you might not even notice that you are in such an isolated island, and of course you would never leave it. So the result of these experiments will differ whether you hit the an isolated island or not, because if you do only these ratios for the web pages within this island will converge to something that is not zero, and of course ranks of all pages outside will converge to zero, right? Because t will be larger and larger and number of visitations will stop, right? So clearly there are problems with these two, with these three heuristics. So all three heuristics are actually connected. So let's see how the formula that we have just given. So rho I equals, sorry, let me keep it reasonably tidy. So rho I is equal to the sum of all over all pj that point to pi, and then rho j divided by the number of outgoing links of pj. Let's see what this equation says. Let's assume that we have a solution, and let's also assume that this solution satisfies that the sum of all ranks row K, where K belongs to the WWW, is equal to 1. And of course, whenever you have a solution to the system of equations, one per each web page, right? So we would like that this formula holds for every web page PI. So for every web page PI, its rank satisfies this property. So this is clearly a system of equations, one for each web page PI. So if we have a solution, of course, we can always divide left and right side by the same number to essentially normalize so that all the ranks, if you have any solution, divide both left and right side with the sum of row i's, and you will get a solution in which sum of row i's is equal to 1. So how can we interpret this? Well, let's say that in fact this intuition that we just presented with web surfing actually holds. What would this mean? This would mean that, you see, after long web surfing of, say, T links, I look at next click where I will be, and then clearly we have the following. Assume that, so this is our web page PI, and this is a web page PJ1, PJ2, and so forth, up to web page PJK that point to this web page. And say initially we chose the starting point at random, right, from the web page. Then it makes the following sense to ask. What will be the probability that after T+1 many clicks, we end up with web page at web page PI? Well, to end up at web page PI after T+1 clicks, it means that you had to be here on one of these web pages when T was equal just T clicks, right? Because in order to end up, we are not doing any random teleportation at the moment, just following the links. So in order to be at web page PI after T+1 many clicks, we should have been at the web page, either at the web page PJ1 and chosen the appropriate link that goes to PI, or we should have been at web page PJ2 and chose the appropriate link, and so forth. So if we denote the probability row, let's use another letter. Let us use pi for probability. So what is the probability? Pi, that after T+1 clicks, so this says how many clicks, we end up at the web page PI. Well, this probability is clearly equal precisely to the sum of probability pi that after T many clicks, we end up at PJ, and that after ending up at PJ, we chose the right link. So the probability has to be prorated with the number of outgoing links on the page PJ, and we sum up this for all PJ that point out to PI, right? So the probability to end up here at PI after t+1 many clicks is equal to the sum of probability to end up at PJ1 divided by the number of outgoing links at PJ1, because you may choose wrong link to follow. So if probability that you are at PJ1 is pi PJ, then the total probability to also take the right link will be pi j1 times 1 over number of outgoing links, because that's exactly the probability, right? This guy here is equal pi p sub pj times 1 over the number of outgoing links pj. So this is the probability to be on the right web page pj, and this is the probability to also take the, among all hyperlinks on that page, to take the one that points to PI. But if our intuition was correct, then this probability to end up at PI after t+1 many clicks should be equal to the probability to be there after only t many clicks, because we said that we should have the property that as t increases, they all converge to the same value. So this value that all of these guys converge, right? So limit of pi pj t when t goes to infinity. Well, if you call it rho I, then notice this becomes precisely the formula that we propose. So notice, so this, as I said, first intuition was that rho I should be large if the ranks of pages pointing to PI are large and there are no too many excessive links. But why exactly that formula? Well, this business with random surfing actually explains, because that would precisely correspond to probabilities to be at that web page after large number of clicks, right? And the probability to end up at that web page clearly is a good measurement of the importance of that web page. So I hope you understood now well all of the three heuristics, but we also pointed out that actually there is no guarantee that such rows will exist, and we gave two examples how this might fail. First, how it might fail is if you end up at a dangling web page that has no outgoing links, like a PDF document. So that's first problem, right? Second problem is it can be even worse. You might end up in an island of a group of web pages that have links from one to the other. So the graph of hyperlinks is, say, strongly connected. You can reach any web page from any other web page, but there are no outgoing links. So if this island is large and you are doing your surfing, you might not even notice that you end up in such an island, and clearly existence of such an island prevents the convergence of random surfing, because after all, on the whole worldwide web, there can be several different such islands. And then as you do random surfing, once you might end up in one island, in another web surfing, you might end up in another island. So there is no way that the ranks can converge, because a number of visitations of the pages, if you end up in this island, will be the ratio over number of visitation over total number of clicks will be non-zero only for web pages in that island. All other web pages, eventually the number of visitation freezes, and then as t increases, the number of clicks increases, the ratio of number of visitations divided by t, right? So number of visits divided by t would go to 0 if you are not, for all web pages that are outside that island. So this has to be also handled. And there is another problem of convergence of this. So let's look at the third heuristics in which we do lots of smaller experiments, right, and clicks, but we do them a large number of times t. And we would want that when n and t goes to infinity, the number of times we end up, so we want number of times ending on pi divided by total number of experiments. We want this to converge. But notice, if we fix n, and if it happens that the World Wide Web is, say, a bipartite graph, right? Then clearly probability, the number of times to, if you start from here, the number of times to end up here, if the number of clicks is odd, then this will be 0, right? Because you can be here only after even number of clicks. You have to change the side and then go back and so forth. At each odd click, you will be on the left side of partition. For each even click, on the right side of partition. So if you fix n and let t goes to infinity, things would not converge. And bipartiteness, of course, World Wide Web is not bipartite, but this problem can happen in a more general setup. Namely, let's consider the whole World Wide Web as a graph with the pages as vertices and hyperlinks as edges. Such a web page would be called periodic if all loops that start at web page and end at that page, the number of vertices visited is divisible by a fixed number k, right? Maybe k is 17. So if there exists a web page will be periodic if all the closed cycles of hyperlinks that start at that web page and end at that web page are divisible by 17. Now, clearly, probability to go to this web page back after 18 clicks is 0, because any number of clicks to end up back at this web page has to be divisible by 17. So the structure of the graph doesn't have to be bipartite, but it has to be, it could be periodic for some. Of course, bipartite graphs are periodic graphs with k equals to 2, right? Namely, all closed links have to, all closed loops, the number of vertices has to be odd to return back. Okay, so now So there are problems with this intuition, and clearly our random surfing, as we describe it, doesn't work. So we have to alter the way how we surf web so that neither of these three problems can happen, right? So the presence of dangling web pages will not hurt. The presence of islands will not hurt. And the presence of periodic web pages also will not hurt. And this is accomplished by a single trick, ingenious trick that Page and Brim invented, that not only solves all these three problems, in fact, it solves all the problems, but not by a technical mambo jumbo, not by some technical surgery on the links, but by something that itself is an excellent heuristic. You see, because one might argue that no web surfer keeps clicking on the links on web pages, so we allow the web surfer to become impatient. So this is what he does. He starts at a web page and keeps clicking on the links, but then every now and then, with certain reasonably small probability, he gets impatient, and instead of following link here, he jumps to a completely random other web page. And if he ever hits a dangling web page, he again randomly jumps to an arbitrary other web page. So essentially how this is technically solved is you take a number, how did we denote it? I think alpha, right? Alpha that is close, it is smaller than 1, but reasonably close to 1. We will see later how close we will take alpha. And then the surfer does this. Whenever he ends up at a web page, with probability alpha close to 1, he chooses to follow the link. But he can also, with probability 1 minus alpha, choose to jump to a randomly chosen web page, right? So each time he gets to a web page, he tosses a coin, and that is highly biased, right? That tail comes with a large probability, in which case he follows the link, a randomly chosen link on that web page. And if it comes head, then he doesn't follow the link, but jumps at a random web page. So this is clearly very kind of, it's a heuristic, right? Because it really describes a reasonable form of a random surfer. And what's absolutely amazing is that if we change the surfing protocol in this way by randomizing how long you follow the links, all problems are solved, and the intuition for the page rank works. Namely, with this web surfing, in fact, the number of visitations of each web page after too many clicks will converge regardless of the particular choice of the links to follow, right? And if you do this for a long time, probability to be at a particular web page, if you stop there, will also converge. So, and the solution of the system of equations, so the first heuristics, in fact, will have a unique solution. So let us now see how this is resolved kind of in a more formal way. Let me go back to the slides and we will continue from there. So let me just briefly look back at the formulas that we had, and we will explain why we change things in this way. Okay, so this is the original matrix representation of the equations that look like this. If we denote ranks by, how did we do it? Let's call rank row I. That's rank of the web page row I. You remember this was equal to the sum of rank of J over number of outgoing links on J over all PJs that have outgoing links to PI, right? That was the condition, that the set of conditions that we wanted satisfied. Well, notice that this set of conditions can be compactly written as vector row transposed is equal to the vector row transposed times G1, right? Why is this so? Well, let me see, maybe it's on the next page. No, let me just go back a little bit more and show you where this comes from. Okay. Okay, here it is. So if you are multiplying rows transposed, because we take them as a row vector, so we have to, vectors are always represented as columns, so we have to transpose it to get a row vector. If you, if you multiply this vector by a matrix G1, you will get a vector, a row vector, right? Because here you have row, here you have a matrix. So since you have only one row on the left, the output will be just one row, a transposed vector. And so let's see here at the jth place what you get. At the jth place, you have to multiply row transposed with the jth column of G1. But the jth column of G1 consists of all zeros except for the rows rows I such that I points to pj, right? So, but this, right, if you multiply, zeros will kill all the rows except for the rows that corresponds to I that point to j. So consequently, you will get precisely this sum. So only on those that web pages that point to pj, then you will have non-zero entry, which is this reciprocal, and it will multiply rank here, and you get precisely that. So quickly going back to the, let me see, this was probably slide, maybe, let's see, it should be probably, let's try this one. Okay, this is further down, so maybe it is, this is still, let me see, what do we have here? Okay, so this is, we can go a little bit back. Here it is. So the first starting matrix was the matrix that had zeros at all dangling web pages, because if pi doesn't point anywhere, right, there is no probability to jump anywhere, so you have only zeros. So the system of equations that we had simply says that rho t time is equal to rho transpose times G1. Now, if you are at a web page pi and there is a hyperlink to a page pj, the probability to choose the right hyperlink is 1 over the numbers of hyperlinks on pi. But then, if pi is, if pi I say is the probability to be at the web page pi, then probability to end up at pj from that page will be precisely, if you multiply this, will be precisely rho j divided, rho I messed it up here. Let me put here j and here i's. Sorry about that. I flipped the meaning of I and so this one I want to erase it. Okay, so this is pi and this is pj, pi number of pi, so that it matches what's on the slide, right? So rho I divided by the number of outgoing links I is precisely the probability to end up at page pj if the probability to end up at pi is rho I, and probability, of course, to choose the right link is the number of outgoing links. So these guys simply reflect probabilities that if you are at page pi, you jump to the page pj, because the probability is precisely 1 over the number of outgoing links. So this matrix has a probabilistic interpretation. And of course, this is also fits well, because if you are at a dangling page, probability to jump to any other page is 0. So now we first fix the problem of dangling web pages. How? by setting probabilities. Instead of 0, we set them to be 1 over n. Namely, if you are at a dangling page, n is total number of web pages. If you are at a dangling web page, then you choose completely randomly another web page, so with probability 1 over n, to jump at that web page, right? So this would be equivalent by changing our graph as follows. So probability to follow, so the weight of this edge is, say, 1 over the number of links on page PI, right? But this is a dangling web page, right? So then how we change it is, instead of making it dangling, we put weak edges. So now dangling web pages will have edges to every single other web page on the web, but the weight of this edge will be very small, 1 over n, because that's the probability. So the weight of edge in this directed graph is the probability to take this this path, right, this edge, right? So we first fix the problem of dangling web pages by replacing a 0 vector with 1 over m everywhere. And again, we can interpret this as probabilities, right, of jumping, of going to that web page. But now we have to address the problem of isolated islands, all right, and the problem of periodic web pages, right? Ones that following the links produces that come back to that web page always produces a loop divisible by a fixed number. How do we do that? Well, remember, these guys are the probabilities that if you are at page PI, to jump to this page PJ, if this is the jth column, right? Now, we change that. Rather than always following only links to these web pages, we do something different, right? We do the following. If you are at the web page PI, then you follow the links only with probability alpha. But this means that probability now to follow a particular link is not 1 over number of outgoing links, but it is alpha to follow a link at all, and then divided by the number of outgoing links. So this gets replaced by that. But then what we do, we also leave the opportunity that with probability 1 minus alpha, we jump to an arbitrary place. So for all web pages, we have to add probability 1 minus alpha divided by n, right? Because if you are at PI, you can jump to any web page with probability. So to jump, the probability is 1 minus alpha, because alpha is probability to follow a link. So you jump with probability 1 minus alpha, and because all the web pages are equally likely, all the entries here will be augmented by adding this, including the web pages that have links, because now you have two ways to end up in PJ. You can end up, if you are at PI, you can end up by either following the link or by randomly jumping there. So the upshot is that, so this is fixing the dangling nodes. And the second, when we add teleportation, so notice all entries, there are no zeros anymore. So all web pages get at least probability 1 minus alpha m to end up there by teleportation. And those that do have links on at page PI, right, then they get the probability alpha divided by the number of outgoing links plus 1 minus alpha divided by m. And our claim is that now with this matrix, which is called the Google matrix, right, the equation ranks transposed equals ranks times G indeed have this system of equations, right, because rows are vectors. This system of equations always has a unique solution, right? So solving the equation that looks like this, rho I is equal sum over all j that belong to World Wide Web of 1 minus alpha sorry, let me just see, rho I, so we can either be, sorry, just one moment, let me not mess up this. So here we will have this divided by n, right? Plus, times rank rho j plus sum over all j that do point to I of alpha over the number of outgoing links on pj. So this is what you get, right? This time if you multiply this vector, oh God, what happened here? Oh, boys. I hate this software. Oh man. Okay, so right, because now you are multiplying rows. You are multiplying rows. So here is row 1, row 2, all the way up to row, I call it, and I switch between n and m. M is the number, so up to row m. And then here you have a matrix. And then instead of zeros, now everywhere you will have 1 minus alpha divided by m, except somewhere will also, you will have 1 minus alpha divided by m plus alpha divided by the number of outgoing links of pi. That's on the, when you are on the row I. And when you multiply jth column with this row, that's precisely what you get. Okay, so now the question is, why is it the case that this system of equations, right, that in fact if you assign ranks in this way, the solution is unique, exists, and it is unique. And that's our next topic to show this. Now, there is now a pretty lengthy discussion here that deals only with one issue, right? Because let me show you what's the problem with this matrix here, right? The problem with this matrix, oh gosh, is that it is no longer sparse, right? Because we have non-zero entries absolutely everywhere. The problem with such a matrix is that it's of size trillion by a trillion, right? So a dense matrix of this size you cannot even store on your computer, right? But from this expression, you can also see that in fact you don't need to store that matrix, because, and this is what the next steps show, multiplying such a matrix with a vector is reducible to, let me just move forward, you can look on this, to multiplying from the left with a vector v, this expression. Now notice, so d is the indicator vector of zeros and ones only, that has zeros everywhere except on dangling nodes, right? Where it has one. So this is just a vector outer product with vector of all ones. So the point is that if I multiply, I will not directly multiply v by g, I will multiply v by g1, which is the starting matrix, which is sparse, and then I will multiply this, but this is extremely simple expression because this consists only of ones and zeros, right? And it is sparse because there are only these when you have dangling nodes. And this here simply says add to all entries that you get 1 minus alpha divided by m. So this was, I derived it last time, but it's not so crucial if you are not so familiar with this, but you should take a look at and try to figure it out. It's just basic matrix algebra, but the whole point of this representation is that multiplying g by a vector from the left can be done fast despite the fact that the g is not sparse. And this is another kind of bravery of Page and Brim, because the matrix they produced was not sparse, but they didn't give up and found a way to quickly evaluate the products despite the fact that the matrix is not sparse. So next thing, and here is the derivation, but as I say, please do go over it, but it is not the most crucial part. So now the question is, why the matrix G that corresponds to transition probabilities of an impatient surfer, why does G work? Well, the reason for that And of course, why is a solution unique? Remember, the page rank has to be unique so that there is no any arbitrariness in assigning the ranks to web pages. And the reason why this holds is very general, and it has been known for centuries, and because it's a statement about something called Markov chain. And Markov chains are extremely important in computer science. After we finish the page rank, we will show how Markov chains are applied to speech recognition. So this is really bread and butter of every computer scientist. So what is then a Markov chain, or also called discrete time Markov process? Well, any Markov chain is given by a set of states, and we will only consider finite Markov chain where the number of states is finite. In our example of random surfer, the state I is essentially corresponds to the random surfer at this moment is on the web page, looking at the web page PI. So state of a Markov chain for the random surfing can be interpreted as what web page are you in? And so the number of states is equal to the number of web pages. What else do we have? We also have a raw stochastic matrix G. What does it mean, raw stochastic? It means that sum of all entries in every single row is equal to 1. So that this matrix can be interpreted probabilistically. How do we do that? So a Markov chain starts in a state that can be chosen, initial state, that can be chosen randomly out of all available states. So in the case of the random surfer, we would allow him to start surfing at an arbitrarily chosen web page. And what happened, and then, but that web page, in the case of random surfer, is chosen with probability 1 over n. So we have also initial probability distribution of what is the starting page of what is the starting state of the Markov chain. In our web surfer, we said, so the states are being at a web page, and the initial probability to be at any web page is equal for all web pages equals 1 over n. But in general, it doesn't have to be that way. Then what happens, next moment, which corresponds to 1 click, Markov chain from the starting state can switch to another state. So say this is state Si, and here this state is Sj. And this transition is completely random and is governed by the matrix G. So if you look at the matrix G and you look at the row that corresponds to state Si, and you look at the column that corresponds to the state Sj, right? Because the size of the matrix is number of states times number of states. And this entry here, we will denote as, how did we denote? Let me keep the same notation. What did I use? Sorry, let me. well, okay, I might have used something else, but let's call this entry here probability to switch from state I into state J. So this probability is the entry Gij in the matrix G. Right? So entry of the matrix tells you what is the probability if your chain is a state of I, next moment to be in the state of J. And then you continue in this way, right? For a long time. So notice in our new surfing model, right? In our new surfing model, probability to switch from page, yeah, let's call this pi rather than, how did I call it? Oh, well, it's not that important. So probability to go from page pi into page pj, right, which will be this pi of ij, which is the same as the entry gij in the matrix, is, so what is that probability? Well, there are two cases. First case is the probability is 1 minus alpha divided by m plus alpha divided by the number of outgoing links on pi, and this is if page pi points to page pj. And it is equal just 1 minus alpha over m if pi doesn't point to pj, oops, doesn't point to pj, right? Because the only way to get from pi to pj, if pi doesn't point to pj, is by random jump, right? And probability of a random jump is 1 minus alpha, and there are many web pages, so probability to end up exactly at pj is 1 minus alpha divided by m. So our Google matrix is an example of a matrix that corresponds to a Markov chain, right? Because each entry Gij gives the probability, if you are at page pi, to end up next turn into pj. So note, when we do random jumps or follow links, probability to end up at pj doesn't depend on how you ended up in pi, right? So if you are at the page pi, probability to end up at the page pj doesn't depend at all how you ended up at pi, from which other web page. It only depends on whether there is a hyperlink from pi to pj or not. So the transition between the states of a Markov chain is completely local, memoryless. So Markov chain, when it changes this one state into another, the probability depends only what state are you in and what state you are going to, without any reference to the past history of the Markov chain. Okay. And as I said, the state x0 at which the Markov chain starts can be also random. So let's denote the probability distribution of the initial state by Q0. In our case of random surfer, Q0 is an identity 1 over m, or everywhere 1 over m times, right? Because all web pages are equally likely, but as I say, this need not be the case. X0 can be an arbitrary distribution, and even this distribution can be like this: 0, 0, and then at a single place 1, and everywhere else 0. If this is the initial probability distribution, how do we interpret this? What do you think? So this is the probability to be in the first state, probability to be in the second state. This is probability to be in the ith state, and so forth. So what does this vector 0, 0, 1, 0, 0 mean? How this means that the Markov chain is always starting where? What do you think? Exactly. We have, Anthony says, we have a fixed starting point at page I. That's exactly right. Right? This vector would say that the starting point is always page I. And lo and behold, an amazing feature of the Google matrix is, as we will see, that after a long evolution, the probability distribution of the states will be independent of the initial probability distribution of states. So starting at a random state and starting from a particular state always, and evolving right by doing these impatient random clicks will produce the same probabilities. Okay, so let us see. Let's now denote by Qt the probability distribution of states at an instant t. Then what is the probability distribution of states and instant t plus 1? Well, so these are your choices for the states at instant t. And you know the probabilities probabilities to be at any of these states. In our random surfer case, probabilities to be at any web page, say. What are then the probabilities to be at a page pj in the next state? Well, the probability is equal. Probability to be at P1 times the probability to take the link to Pi, which is G1I, right? That's the first row and column J, right? This is the probability. So we are starting at, say, state P1. So that's the first row. And we are asking what's the probability, what happened here? To end up here at Pj. Well, that's exactly G1J. If you are at P2, then this will be the probability to end up at Pj, and so forth. So this column will give you these probabilities, and of course, the total probability to be in Pj is the sum of probability to be at P1 times making the right click, probability to be at P2 and make the right transition, and so forth, up to probability to be at the last web page on the web times probability to make transition to Pj, which is precisely this, right? But notice what this says. If I write this oops, instead of rho, I'm now using Q. So let me continue in this way. So this means that the vector, oh gosh, sorry. So vector Q of probabilities at instant t plus 1, this simply says is equal Q at instant t times the matrix G, right? Because this is exactly the outcome of multiplying, right? The jth entry in this matrix will be precisely this sum, because this is the product of the row of Q's times the jth column of G. So we get that the probability distribution after instant t plus 1 is exactly probability of distribution at instant t times G, right? So now, if you chain these t times, right? Because what do you have? You have Q0, then you have Q1, which is equal Q, let me be consistent. So then you have Q1, which is equal, oh gosh, why do I keep writing rho? Which is equal to distribution Q0 times G, and then I have Q2 is equal Q1 times G, and then I'll have Q3 is equal Q2 times G, and so forth. But I can chain these equalities, and I get that this is equal to Q0 times G, right? Because I replace this by this by that, which is of course Q initial distribution times G squared. And here in the very same manner, I get this is Q1 times G, which is equal to Q0 times G, which is of course Q0 times G cube, and so forth. So the probabilities evolve, right, simply by this is what we just had, right? Simply by taking so after t many steps, the probability distribution is the initial probability distribution times the G to the power t, where t is the number of iterations, right? Now, so our random surfer is an example of a Markov chain. States are web pages. He starts from a randomly chosen web page, so initial probability distribution is 1 over m. Yes, so sorry, I didn't notice the question. Andy, yes, so Gij is the probability of going from I to J. That's correct. What do we have? The probabilities, as we know, is if there is a link is alpha over divided by the number of outgoing links on Pi, plus the probability of a direct jump. So in our case, Gij is probability of following the link plus the random jump if page pi points to page pj. If not, then it's just 1 minus alpha divided by n. So now, and if pi is a dangling web page, then gij is of course, always equal to just 1 over n. Okay. So now back to general Markov chains. And this now introduces some general stuff about graphs and matrices. Okay. So assume that you have a weighted graph. And if there is an edge, this means that the weight ij, so this is I, this is j, is bigger than 0. And if weight is 0, it means there is no link, right? To such a graph, you can assign a matrix of just zeros and ones, which would be essentially the adjacency matrix if you ignore the weights, right? So if you take sine of m, you will get 1 whenever the weight is positive. So there is a link, and 0 if there is no link. So you just get adjacency matrix for that graph. Now, this adjacency matrix is very useful. You can prove the following things. The following thing: if in your directed graph there is a path from I to j of length k, right? So there is a path of length k. That happens just in case this adjacency matrix, if you take it to the power k and you look at ij, if this entry is not 0, so there will be a path just in case the entry at position ij of the kth power of the adjacency matrix is not equal to 0. Lo and behold, you can show that this entry is precisely the number of directed paths from pi to pj that are of length exactly k. This is really useful to know. In general, it's an important connection between graph theory and matrix calculus. Okay, we say that a directed graph G is strongly connected just in case for any two vertices ij, there exists a directed path in G from pi to pj. And because this has to hold for all I and j, this should also hold for all j and I. So a graph is strongly connected just in case for any two vertices there is a path, directed graph. There is a path from I to j and a path from j to I. Now, definition. A Markov chain is irreducible if the graph corresponding to its transition probabilities matrix is strongly connected. Right? So notice in our original analysis of the random surfer, when we just considered the existing links without this random jumping, this the corresponding Markov chain wouldn't be reducible because there is no reason that for any web page you whatsoever on the web, you can reach every other web page just following links. This is obviously patently false, right? So the Markov chain is irreducible if the graph that corresponds to in-transition probabilities is matrix is strongly connected. I claim with the random surfer, lo and behold, this Markov chain is irreducible. So why is it the case that with a random surfer, when we got weak links, so for low weight but non-zero weight, from all dangling web pages to every other web page, and we add weak links from every other page with links to all other web pages that do not have this link. Why is the corresponding graph strongly connected? Why is this the case? So why is it? So what did we do essentially? If you represent the graph of the World Wide Web, so the pages, originally we had edges only when the hyperlinks were present and the weights of the edges were 1 over the number of outgoing links on PI. But then we made this graph complete by adding weak edges between any 2 points, right? So even if this page doesn't have a hyperlink to that page, it will still have an edge, but the weight will be low. It will be just, right, 1 minus alpha divided by the number of web pages. So why is this graph strongly connected? Why does it have exactly one strongly connected component? What do you think? What is, after we add these weak links for random jumps, what does the graph look like if you ignore the weights? How do we call the graph that we obtain in this way? Complete graph, exactly, because now every 2 nodes are connected, maybe with links with very low weight, but and a completely connected graph is obviously strongly connected because any 2 points are connected by a path with how many edges? In a complete graph, what is the minimal number of edges to connect a vertex I with a vertex G, with a vertex J? 1 edge, exactly. So trivially, our Markov chain is irreducible because the underlying graph is the complete graph, and thus it's strongly connected. Okay, now we have another property of Markov chains, namely, if you look at the corresponding graph, so these are the states. In our case, they are web pages, but they are the states. And we say that a state is periodic with period k if every closed cycle its length, the number of edges, is divisible by k. And graph is aperiodic, and the Markov chain is aperiodic if there are no periodic states, right? So for no state is it true that every loop containing this state is divisible by a fixed number k. And lo and behold, tell me, why is our Google PageRank graph aperiodic? Why is it the case that there is no web page so that every loop through the corresponding graph, the number of edges must be divisible, for example, by 3 or any other number? Why this is not the case? Will this be costly since G is expected to be a huge? What do you mean by costly? You mean making the graph complete? Well, that's a very good point. The complete graph is costly, but manipulating it is simple, because multiplying that, the vector with that matrix, right? G, we saw, and this is this tedious calculus that we did last time, it's reducible to a multiplication of a vector by a sparse matrix plus some easy calculation involving only 2 vectors without, so everything is reducible to a simple calculation. Probability multiplication, I mean. Yes, it is costly, but that's where we do a trick. Namely, okay, so the graph that corresponds to Google PageRank graph, right? Why is it aperiodic? Why is it not the, why is it true that there is no web page so that every loop that goes back to web page is divisible by, say, 3? Why this is impossible? In fact, for every web page, for what values of k are there loops ending, starting and ending at that web page that contain exactly k edges? Is it true that in Google PageRank there are always loops of size 2? Well, we have a weak link between any 2 nodes. So here is a loop of size 2. There is also a loop of size 3. Well, you go visit arbitrary web page because it's fully connected. You can go to any web page. Then you visit arbitrary other web page, and then you return. Clearly, because the graph is fully connected, the corresponding Markov chain is exactly, that's what James says. So clearly there is a loop of size k for any k bigger or equal than 2. So the underlying graph is aperiodic. Now comes the place, the only place where Page and Brim had to know some very basic probability and statistics. Namely, they knew that there exists a probability distribution R, so that when you multiply it with a matrix G, you get back this probability distribution. Just in case G corresponds to a Markov chain that is both irreducible, which means it is strongly connected, all the states are connected through a path, and it's aperiodic. So that's a general theorem about Markov chains that Page and Brin learned from Motvani in his course on randomized algorithms. And that's all what they remember, because probably they never learned the proof of that fact, even though I'm sure Motvani showed the proof in class, but it's enough just to know the theorem. Any finite, irreducible, and aperiodic Markov chain has the following properties. For every initial probability distribution of states Q0, the value of the probability distribution after T many transitions converges to unique stationary distribution Q, to a fixed vector, right? Which is independent of the starting distribution. So no matter how you choose initial web page, after a large number of clicks, probability to be at any given web page at that moment is independent on how you started and how you chose the links, right? Because if T is large, this will be always almost the same, and as T grows larger and larger, in fact, it converges to a fixed distribution, which we call stationary distribution of the Markov chain, right? Because why is it stationary? Because if you are in that distribution and then you apply one transition by matrix G, you get back exactly the same distribution. And moreover, this distribution Q can be obtained iteratively, starting by any initial distribution, say uniform one over M for all web pages. If you multiply this distribution with sufficiently large power of G, of course you won't get exactly Q, but if T is sufficiently large, you will almost be there at the stationary distribution. Moreover, okay, here I didn't put transpose just because you have T as the iteration and transpose messes up. Here we assume that Q's are just the raw vectors. Okay. Moreover, if you do transitions for very large number and you do keep count how many times you visited a page PI, well, the number of times you visited PI divided by the number of total clicks, the length of evolution of the Markov chain, will be precisely the ith coordinate of that stationary distribution. So the general theorem of the Markov chains implies that indeed one is the left eigenvalue of the Google matrix G, because as we just demonstrated, G corresponds to a irreducible and aperiodic Markov chain, right? And one can show that one is in fact the largest eigenvalue. All other eigenvalues by modulus have to be smaller or equal than 1 because they can be complex numbers. So 1 being the largest, meaning the largest in absolute value. And this stationary distribution is unique. So there is only one eigenvector that corresponds to eigenvalue 1. And distribution Q can be obtained by starting with an arbitrary initial probability distribution Q0 and then finding the limit of Q0 multiplied by the kth power of G. Now, notice, and this is to answer Pable's question. This, as it stands, is an extremely expensive proposition because to find the kth power of a non-sparse matrix would be a killer. But we now use the fact that matrix multiplication is associative. So Q0 times G, and then this times G, and then this times G, and so forth. If we do this K times, this is in fact the same as Q, as Q0 if you multiply it with G to the K, right? Because you can, right? Because what is this? G to the K is G times G times G times G and so forth. But you can put the brackets any way you want because matrix multiplication is associative. And as we mentioned, even though G is a full matrix, multiplying it with a vector can be done in an extremely fast way. This was this kind of messy calculation that I showed you how to do vector matrix multiplication in case of Google PageRank. So what does Google do? Well, what initially did? Well, they start with 1 over n, right? When n is the number of web pages on internet. So these are all extremely small numbers. So one has to be very careful not to get underflow. Now this is smaller than probably 1 over a trillion. So it's all coordinates are very small and you have to be careful when you do your multiplications. Okay. So this is their Q0. And then they just do this fast multiplication by G, get the resulting vector, which would be this vector, and then they multiply that vector again with G and keep doing that K times. And initially it would take about a day to compute the page rank. How big should K be? Well, this is a very interesting question. The size of K that is needed depends on our alpha. Closer alpha is to 1, slower the algorithm converges, right? But notice alpha is probability to follow links. So if alpha is not very close to 1, any surfing session will be short. Let's see what will be the expected value of a surfing session. Well, number of links followed between 2 random teleportations is 0 with probability 1 minus alpha, because probability 1 minus alpha is probability to jump randomly, right? It has one link followed with probability alpha times 1 minus alpha, right? Because alpha is probability to follow a link, and then random jump, which is 1 minus alpha. You follow k links with probability alpha to the k, and then you random jump, so it's 1 minus alpha. And this, you can pull out alpha times 1 minus alpha, and notice you again get this triangular sum of 1 plus 2 alpha plus 3 alpha squared plus k times alpha to the k minus 1 and so forth. And remember, we did this in several ways and found that this is 1 over 1 minus alpha squared. But when you multiply with this, you get alpha divided by 1 minus alpha. So Google uses alpha that is only 0.85, which is not very close to 1. What does this mean? And how did they get it? They got it empirically, by trial and error. And what did they, but analytically you can see, using this formula, if alpha is 0.85, you will follow just about 6 links before you do a random jump. So now the question is just following links 6 times and then random jumping enough to reveal the structure of the internet? Enough to reveal what the important web pages are? It's kind of clear that if you follow the link with higher probability, say 0.95, your random surfing will be much longer, and in fact you would capture the structure of internet in more accurate way. But with alpha 0.85, it turns out that the number of iterations to get reasonably stable page ranks is about 50. And if you have a matrix, sparse matrix of size 1 trillion by 1 trillion, then 50 iterations, probably we could do more nowadays than when the Google people started. Now, but do we sacrifice much by keeping alpha 0.85? Which means making, excuse me, making on average only 6 link follow for click 6 clicking on average only at 6 links before we jump. Well, in the beginning of the 20th century, a sociologist wanted to investigate how connected people in America are. So assume a graph where each vertex is a person in the United States who is alive or adult in, I think it was sometimes in the 30s. And you put a link if person X knows person Y. And he wanted to see how well connected is the link. What's the probability? Is it true that you can visit, that you can reach any person in the United States from any other person, always going only through people that this person knows? So he did the following experiment. He sent letters that were addressed to some people in in the United States that he found from the telephone directory book, and he only put their names, the city where they live, and their occupation. And I don't remember exactly how many letters he sent, I think a couple of hundred of letters, and he sent such a letter to all of his friends and asked them in an accompanying letter to forward this letter for that unknown person to any friend that they might suspect who could know that person. And shockingly, 1/3 of all of the letters arrived to their destination within a couple of months. And I guess people were looking, oh, do I know that this person is from New York? Do I know someone in New York? Okay, I'll send a mail to that person in New York. The receiving person will look, oh, this guy is also in New York, but he is a lawyer. Okay, do I know a lawyer in New York? I sent him that letter. Now you have a lawyer in New York, so he is actually quite likely to know, well, if not all lawyers, but to know another lawyer who eventually might know a lawyer that knows that person. And shockingly enough, the number of forwarding was 6 on average. And this is known as 6 degrees of separation. So any two people in New York on average, it takes a path, not only that they're connected, but it takes only a path. So for example, between myself, if I was in New York, there would be 5 more people that I can use as intermediaries to send a letter to Donald Trump. I won't tell you what I would say in that letter, but you can guess. So anyhow, so 5.7, because of this 6 degree of separation, is actually good enough, or at least it was the initial value. Okay, so we are out of time. We will very briefly finish with some refinements of PageRank, and then we are going to move to Markov chains for speech recognition. So this is, look, Google PageRank, so Brim and Page were not mathematicians. They knew a very basic theorem on Markov chains, and they made 1 billion. So please buy their tricks. So read carefully the PageRank and don't worry too much about the derivations, right? But worry about the heuristics and how and why PageRank works. Okay, so we continue next week. I'm trying to finish the list of topics for you, and I'll have it on Monday, I promise. So guys, have a good week, and I'll see you on Monday in an hour. Oh, you know, I forgot to look at Piazza. Are there any comments there already? If that's the play, I promise I will look at Piazza. Sorry if I didn't answer. I simply forgot to check that. I had a tutor for 3121 who did all of the tracking, but I will look what questions are there and I'll answer all of them. Yeah, there is one, and yeah, song made, and I will find the link again. I emailed it to everyone, but I will find the link and email it and put it on the web page. Okay, please use it. discuss the material. It's a hard material, but important and really beautiful material. I promise you will learn a lot of extremely important algorithms that are making billions nowadays. So if you want to be a competent computer scientist, you should at least know of these algorithms and basics, how they work. Okay, so then I will see you next week, and I will check Piazza right now. Okay, see you guys. Bye-bye. Guys, I'm having office hours in an hour, so you're more than welcome to come and ask me questions.